Greetings, students. Today, we embark on an intellectual journey into the world of algorithms through an intriguing problem: valid parentheses, as defined by LeetCode Problem 20. This challenge presents us with a string composed solely of the characters and. Our objective is to ascertain whether this string is valid, specifically whether every opening bracket has a corresponding closing bracket in the correct order. For instance, consider the input string. This string is deemed valid as each opening bracket is aptly closed by its respective counterpart. The parentheses is closed by and the bracket by. Our goal is to return a Boolean value, true if the string is valid and false if it is not. Let us delve into the intricacies of this problem and unravel the elegant solutions that lie within. A stack is a crucial data structure that follows the last in, first out, or LIFO principle. This means that the most recently added item is the first one to be removed. When dealing with balanced parentheses, a stack becomes incredibly useful. It helps track opening and closing symbols like parentheses, brackets, or braces in a string. The goal here is to ensure that each opening symbol has a corresponding and correctly ordered closing symbol. For instance, in the string ray a plus b times c, the parentheses are balanced, while in a plus b has c, they are not. To check for balanced parentheses, we can iterate through each character in the string. When we encounter an opening symbol, we push it onto the stack. Upon finding a closing symbol, we check the stack. If the stack is empty, it means there's no matching opening symbol. If it's not empty, we pop the top element and check if it matches the closing symbol. After processing the entire string, if the stack is empty, the parentheses are balanced. This method effectively uses the stack's LIFO property to maintain the correct order and nesting of symbols. To check if parentheses in a string are balanced, we can use a stack. This is like a real-life stack of plates. You can only add or remove the top plate. First, we initialize an empty stack to keep track of the opening parentheses. We also create a mapping of opening to closing parentheses, like matching a left parenthesis with its right counterpart. As we process each character in the string, if we find an opening parenthesis, we push it onto the stack. This is like placing a plate on top of our stack. When we encounter a closing parenthesis, we need to check if it matches the most recent opening parentheses. If our stack is empty at this point or the parentheses don't match, we return false, indicating the string isn't balanced. Finally, if we've processed all characters and our stack is empty, we return true, confirming that the parentheses are balanced. This approach ensures we keep track of the order and matching of each parenthesis correctly. Character mapping for parentheses is a vital technique for understanding how different types of parentheses relate to one another in an expression. In programming, parentheses are used to establish precedents in mathematical calculations, group elements in data structures, and manage function scopes. To effectively track which opening parentheses correspond to which closing ones, we use a systematic approach. This ensures that every opening parenthesis has a matching closing partner. This concept is especially important in parsing expressions and validating syntax in programming languages. For example, when a compiler processes code, it needs to confirm that all parentheses are balanced and correctly nested to prevent runtime errors. The method commonly used for character mapping involves a stack data structure. As we encounter opening parentheses, we push them onto the stack. When we find a closing parenthesis, we pop the top element off the stack to check for a match. If the parentheses are balanced, the stack will be empty by the end of our expression. This efficient technique helps developers catch errors and maintain the integrity of their programs. In this slide, we have a function called map parentheses, which is designed to help us work with parentheses in a string. First, we initialize a dictionary called mapping, where we define an open parenthesis as open and a close parenthesis as close. This helps us understand what each character represents. Next, we prepare an empty list named result, where we'll store our mapped values. As we go through each character in the input string, we check if it is a parenthesis by looking it up in our mapping dictionary. If it is, we append the corresponding value, either open or close, to our result list. Finally, after processing the entire string, we return the result, which now contains the mapped representation of the parentheses. This function effectively translates parentheses into a more understandable format, making it easier to analyze their structure in our input. Iteration through a string refers to the process of accessing and processing each character in a string, one at a time. Think of a string as a row of boxes, each holding a character. When we iterate, we systematically open each box in order. We often use loops, like for or while, to do this, allowing us to perform specific operations on each character. This technique is essential in programming. Whenever you're validating input, searching for a specific word, or modifying text, iteration is usually the first step. For instance, if you want to check if a sentence contains a certain keyword, you'd loop through each character to find it. At a high level, iterating through a string means using a loop that starts from the first character and goes to the last. Inside this loop, you can access each character by its index, which lets you check conditions or make changes. This simple yet powerful approach is crucial for working with string data and is foundational for more complex algorithms. Understanding this concept opens the door to tackling a wide range of programming challenges. The function displayed here is designed to iterate through a string and return each of its characters in a list format. Let's break down how it works, step by step. First, we initialize an empty list called char list. Think of this list as a container that will hold each character from the input string. Next, we use a simple loop to go through every character in the input string. For each character, we add it to our char list. This is like gathering ingredients for a recipe. Each character is an ingredient that will mix together in our final dish. Finally, once we've gone through the entire string, we return the char list filled with all those characters. This function is a great example of how we can manipulate strings in programming, allowing us to break them down into manageable parts for further processing or analysis. To solve the problem of validating parentheses, we can effectively use a stack data structure. The goal is to ensure that every opening parentheses has a corresponding closing parentheses in the correct order. First, we initialize an empty stack. This stack will help us track the opening parentheses we encounter as we move through the string. When we find a closing parentheses, we'll want to check if it matches the last unmatched opening parentheses. Next, we set up a mapping that pairs each closing parentheses with its corresponding opening one. For instance, a closing parentheses maps to an opening parentheses. As we iterate through each character in the string, we push opening parentheses onto the stack. When we encounter a closing parentheses, we first check if the stack is empty. If it is, we know there's no matching opening parentheses, and we can return false. If the stack isn't empty, we pop the top element and check if it matches the expected opening parentheses. After processing all characters, if the stack is empty, this means all opening parentheses matched successfully with closing ones, so we return true. If there are still unmatched opening parentheses in the stack, we return false. The algorithm runs in linear time n, since we check each character once, and the space complexity can go up to O(n). In the worst case, where all characters are opening parentheses. This approach ensures efficient validation of parentheses in a structured way, making it easy to follow and understand. In this problem, we are tasked with determining the validity of a string composed exclusively of the characters end. A string is considered valid if every opening bracket has a corresponding closing bracket in the correct order. Notably, the constraints specify that the length of the string must range from 1 to 10,000 characters, and it can only contain the aforementioned bracket types. These constraints guide our approach to implementing an efficient solution. Provided Python code tackles the problem of validating parentheses, a task commonly seen in computational theory and algorithm design. The function isValid bool uses a stack, which is crucial for managing the last in, first out, or LIFO principle needed for this task. First, we create an empty list called stack, which will hold our opening brackets. We also have a mapping dictionary that maps each closing bracket to its corresponding opening bracket. As we go through each character in the string s, we check if it's a closing bracket using our mapping. When we find a closing bracket, we try to pop the top element off the stack. If the stack is empty, we use a sentinel value hash to prevent errors. Next, we check if this popped element matches the expected opening bracket from our mapping. If it doesn't match, we return false, indicating the arrangement is invalid. On the other hand, if we encounter an opening bracket, we simply add it to the stack. After we've processed all characters, we check if the stack is empty with not stack. This confirms there are no unmatched opening brackets left. This approach runs in ON time and uses ON space, making it an efficient solution that ensures rigorous validation of our parentheses. Let's analyze the time and space complexity of the valid parentheses problem. The time complexity is ON, which means that as the length of our input string increases, the time it takes to solve the problem grows linearly. This is because we need to check each character in the string one by one, ensuring that every opening parenthesis has a matching closing parenthesis. Think of it like reading a book. You can't skip pages if you want to understand the story. Now, for space complexity, we also have ON. This is primarily due to using a stack to keep track of the opening parentheses. In the worst-case scenario, if the input string consists entirely of opening parentheses, our stack will need to store all of them. Therefore, the space we use can grow to match the length of the string. Understanding these complexities helps us grasp how our solution will perform, especially with larger inputs.